All right, on this problem, our goal is to take the derivative of 5x minus 3 all raised to the 8th power. And to do so, we're going to need to utilize the chain rule. It's written off to the right-hand side. Why we need to use it is we have an inner function, 5x plus 3, all raised to the exponent of 8. So that means you can kind of visualize this as maybe like x to the 8th power. That's the outer function. And then our inner function, g of x, is going to represent 5x minus 3. So we're going to take the first derivative, evaluate that at a given value, take the second derivative, and also evaluate that at a given value. Throughout, we're also going to talk about what does that mean for our graph when we evaluate at 1 for both the first and second derivatives. All right, so the first thing we want to do is, using the chain rule, we're going to take the derivative of the outer function. So that means that the 8 comes down in front, and we're going to reduce that exponent by 1. So 8 minus 1 makes 7 for our new exponent. We're going to copy down the inner function, 5x minus 3, and not do anything to that right now. But then afterwards here, you'll notice we have to take the derivative of the inner function. So in this case, our inner function is 5x minus 3. You can take this one step at a time if you'd like and think power rule, or you can think the derivative of a linear function is going to be its slope. So we could say either 5 minus 0, or it's just going to be 5. Okay, we can clean this up a little bit more before we actually evaluate it. What I would think is we have 8 at the beginning here, multiplied by 5 from this last set of parentheses. So 8 times 5 makes 40, multiplied by 5x minus 3 to the 7th power. And that's probably the cleanest we can make our derivative look. Next, let's go ahead and evaluate this at a value of 1. So as we plug in a 1, we're just going to replace the x with a 1. We're going to get 40 times 5 times 1 minus 3 to the 7th power, which will be 40 times, we have 5 minus 3 makes 2 to the 7th power. 2 to the 7th power is 128. And that works out to be 5,120. All right, things to note on this. From the first derivative, when we plugged in a 1, got 5,120. The most important thing, though, is probably that that's a positive value, because the derivative, when we evaluated it, was positive. What that tells us about the graph is our graph is increasing at an x value of 1. If that had been a negative number that comes out, our graph would be decreasing at 1. All right, next up, let's go to the second derivative. Basically, second derivative is taking the derivative of the first derivative. So I'm going to this version of our first derivative, and we'll work it from there. With the constant, I'm bringing the 40 along, and really just focused on 5x minus 3 raised to the 7th power. So again, this works as the chain rule, except for instead of like the original, our exponent's a 7. So the exponent comes down in front. You copy down what was inside the inner function here, 5x minus 3. You reduce the exponent by 1, so I'm saying 7 minus 1 makes 6. And then we multiply by the derivative of the inner function. So the derivative of 5x minus 3 is going to be 5 minus 0 again. All right, the cleaning up we can do is we could say, well, 40 times 7 times 5 is going to give us 1,400. Kind of a big number. And then bring along the 5x minus 3 to the 6th power. All right, so we've calculated the second derivative. Now let's evaluate it at an x value of 1 and talk about what that means on our graph. So again, that's just plug in 1 in for each of our x's. There's only one x in this example. So that's 1,400 times 5 minus 3 makes 2 to the 6th power, or 1,400 times 64, which works out to be a very large number, 896,000. All right, so recognizing what does this mean about our graph, g of x, our graph is going to be concave up. And it's going to be concave up because when we evaluated our second derivative at 1, we got a positive value coming out. If that had turned out being a negative value of some sort, then our graph would be concave down at an x value of 1. All right, I hope this helps out. Good luck with taking these derivatives, understanding the chain rule.